Welcome to Total Network Operations, the project with a podcast dedicated to all of you delivering all the packets. We're here to elevate NetOps, help you make informed decisions for your network and your team, and to facilitate constructive dialogue between vendors, NetOps teams, and across the entire NetOps community. I'm your incredibly grateful host, especially today, Scott Robon. We have another Teen Ops on the Road episode today with Dr. Vint Cerf. Where do I start? Vint is widely recognized as one of the fathers of the internet. He currently serves as vice president and chief internet evangelist at Google, a role he's held for nearly 2 decades. His pioneering work began as a grad student at UCLA, where he was involved in the ARPANET project, the precursor to the modern internet. Alongside Bob Kahn, Vint co-invented the TCP/IP protocols, which form the backbone of today's global internet. In this conversation today, we explore Vint's remarkable career and his insights into the evolution of networking technology. We touch on the challenges and resistance to adopting new technologies like IPv6 and AI, the history and future of the internet, and the ambitious efforts to build an interplanetary internet. We also discuss operational lessons from decades of networking, the role of machine learning in space exploration, and the emerging Artemis Accords that aim to guide international cooperation on the moon and beyond. It's going to be a great discussion. But before we dive in, here's a brief reminder that we're interested in your nominations for guests and candidate topics. We want to talk to the people that have important things to say about NetOps for today and the future. Please provide your nominations via direct message to me on LinkedIn or via packetpushers.net/follow-up. Now let's go to the conversation with Vint. Vint, it's a pleasure to be here with you today. Many people will know who you are, but there are many new and career people that haven't heard of you or the work you've done. Would you please give us a brief introduction on your history? And you don't have to be too brief if you don't want to be. So who are you? Tell us who you are.
What an opportunity, right? How many hours do we have?
As many as you want.
I currently serve as vice president and chief internet evangelist at Google, a title I did not ask for. It was a title I was given after I responded to the question, what title do you want? With the answer, Archduke. And Larry and Eric and Sergey said, that probably isn't a good idea. The previous Archduke was Ferdinand, and he was assassinated in 1914, and it started World War I.
We don't want you starting any new wars,
yes,
right? So,
correct. So they said, why don't you be our chief internet evangelist? And so I've been doing that for very close to 20 years now at Google.
Has it been that long? Wow.
I'm having a lot of trouble accepting that too. On the other hand, part of the reason I'm here is because I have a very early engagement in pre-internet work called the ARPANET, which was an experiment in packet switching run by the Defense Advanced Research Projects Agency. I was a graduate student at UCLA at the time that project was started, and I continued to pursue networking and left with a PhD from UCLA in 1972 and joined the Stanford faculty and continued to do research in networking. And my colleague, Bob Kahn, who had worked on the ARPANET, ended up at ARPA and conceived of an idea that would allow the use of computers in command and control. But the implication of that application was that some computers would be in ships at sea, some would be in aircraft, and some would be in mobile vehicles. And the original ARPANET was built around dedicated telephone circuits connecting the packet switches to each other. Well, we had to use radio for these other scenarios. So he ended up building a mobile packet radio network in the San Francisco Bay Area.
Okay.
And a packet satellite network using Intelsat 4A over the Atlantic to link the western part of Europe to the eastern part of the U.S. And then there was the original ARPANET, which by that time had spread not only across the United States, but to some extent in Europe. So he confronted me while I was at Stanford with this problem of 3 different kinds of packet switch networks that needed to be interconnected in a way that looked completely uniform. And that was the internet problem. And to add to the game, not far from my Stanford office was the Xerox Palo Alto Research Center in Xerox Park. And at that location, in the same year, around 73, Bob Metcalf and David Boggs invented the Ethernet, another packet switch technology, which was different from packet radio and packet satellite and ARPANET. So we had 4 worked examples of incompatible packet switching systems. And it took us about 6 months to figure this out, but Bob and I came up with the TCP protocol, which later was split into TCP and IP.
Mm-hmm.
So for the folks who are listening, I'm this old guy who was around back in the late 60s working on packet switching, and now almost 60 years later, maybe about 55 plus years later, 57, I guess, if we do the math. We have not only an international internet, which we think is serving more than 2/3 of the world's population in a direct way, but lots of people are still taking advantage of internet and the World Wide Web applications, even if they're not directly using them. They're affected by them,
Sure.
or other people are providing them services indirectly. So that's my story, more or less, briefly. I've been around since the beginning of the internet, and I hope to be around for a bit longer.
I do too. And I'll just refer listeners to one of my favorite books of that era is called Where Wizards Stay Up Late, where the growth, the development and growth of the ARPANET is really put together in a very readable way. And getting to know you over the last few months through our conversations has really made that book come alive for me. So highly recommended reading or listening, depending on how you consume books these days.
Well, the author is Katie Hafner.
Yes.
She's a stringer for the New York Times in addition to other things. She's written several books, and they all have been quite readable and quite engaging, including one that was fiction piece. It was called The Boys, if I'm remembering correctly. So highly recommended. I'm glad you like the book.
I will. I had intended to see what else she's written, especially on technical topics, but I'm open to fiction too. So I'm actually trying to listen to more books and fewer podcasts these days. So I'll just record them with you. But,
Fair enough.
Well, so we've set a structure for this conversation where we first want to tackle some maybe forward-looking issues and big picture issues. And then in the second part of the conversation, we may go back to some more tactical and operational things. We reserve the right to play with what we talk about as we go here.
Fair enough.
But the first big item I wanted to throw at you is the concept of resistance to technological change. You know, you came into this at a time in, through your education in grad school where you were creating something incredibly new, and we see all the good pieces of it. I'm sure you ran into some resistance, over those developments. And we see it in other ways today too, with specific examples being IPv6 adoption, network automation adoption, and now rising skepticism around AI, just to cite some specific examples. Can you speak to that? Why do we see some of the big pushback for really important technological developments?
Well, some of this could be summed up in the everybody knows X for some value of X. Sure. I would say I didn't personally experience as much resistance to packet switching as others may have. Let's take as an example. Paul Barron was at Rand Corporation in the 1960s.
B-A-R-A-N.
B-A-R-A-N, that's correct. And around 62 or so, he wrote an 11-volume report called On Distributed Communication. And he invented what we call packet switching. He didn't call it that. He called it message blocks were being switched. Sure. But his idea was that you could use these little digital devices sitting up on top of telephone poles with radios going in all 4 directions. You could digitize whatever the information was that needed to be transported. And I think he was thinking about digitized voice because it was supposed to be a command and control system that would survive a nuclear attack. Okay. So he had the idea of a mesh of these transceivers and store and forward devices and packetized, digitized speech. So he wrote this thing up, and then he tried to get the Defense Communications Agency to consider it. And they rejected it out of hand on the grounds that it would never work. And besides, everybody knows if you're building a network, you should use circuit switching because that's what the telephone system did starting in 1876.
Right.
So he did not succeed in getting anything built. Another individual who explored the same concept and invented the word packet to describe packet switching was Donald W. Davies.
Yes.
Okay.
Yep.
So Donald Davies at the National Physical Laboratory came up with this idea of packet switching, as far as we know, probably independent of Paul Barron, consulted with a linguist to apply the word packet to what was being switched, and then proceeded to build a single packet switch because he couldn't get enough money to build more than one.
Sure.
But he had computers and terminal devices attached to this thing. Because it was just a single switch, he was operating it at 1.5 megabits a second, which is much faster than the ARPANET project, which was only running at 50 kilobits a second.
Sure.
On the other hand, they were using long lines, long circuits across the United States, whereas the single switch was in a single room at the National Physical Laboratory. There was a third guy in this picture. His name is Leonard Kleinrock. So Len Kleinrock at MIT was studying these networks of queues, broke the back of the queuing theoretic analysis of what the throughput and variable delay would be in the network. So he established the mathematical profile and utility of packet switching. So that collection of work drove Larry Roberts, who was at ARPA, the Advanced Research Projects Agency, having been brought down from Lincoln Laboratory, to actually test the concept of a packet switch network. Now, the important thing about this part of the conversation is that ARPA's original motivation was not what Paul Barron was trying to do, which is to build this resilient network that would survive a nuclear attack. ARPA had a different problem. They were funding artificial intelligence research in the 1960s. They had
what's old is new again.
Yeah, exactly. So there were on the order of a dozen universities, the ones you would think of right away. Of course, there were Carnegie Mellon and MIT and Stanford University and so on. And so the problem is that the computer science departments that were doing the research for ARPA kept saying that ARPA needed to buy them a world-class computer every year so they could do world-class research.
Sure.
And of course, ARPA couldn't afford to do that for a dozen universities because computers were $1 million propositions. So they said, well, we're going to build a network and you can share your resources. So, and oh, by the way, we're going to fund everybody. So instead of withholding your results to have an edge in a competitive way to get contracts for the following year, share everything, share your software, share your computing capability and your ideas, and we'll advance the state of the art as quickly as we can.
Sure.
But to do this, they had to build a network. So Larry built the ARPANET, and the contract for that went to a company called Bolt, Beranek, and Newman. Now, that's a long way of bringing you to the point where people were enthusiastic about building this thing. So the only resistance I think we had was from the schools that would prefer not to have their computer resources used by people at a different school.
Sure.
But ARPA was paying for it, so it is what it is. By the time I got involved, there was enormous enthusiasm for this idea and great curiosity to see if it would actually work.
Sure.
So the consequence is that I didn't encounter a whole lot of resistance personally during the period of that work. You mentioned IPv6, and the short story there is that when Bob and I were doing this work in 1973, we thought it was an experiment, and I figured that we weren't likely to have very many national scale networks in this experimental period. We had 3 already. One was just local. It was the Packet Radio Net. Packet Satellite spanned the Atlantic. The ARPANET spanned the entire U.S. plus some of Europe. So we developed an addressing structure called IP version 4, which had 32 bits of address space, 8 bits for network, and 24 bits for whichever computer was on that network. Well, that would have been 256 networks. I mean, it didn't strike us as likely that we would build that many networks to do the experiment.
Interesting.
We only had 3 that we had control of. On the other hand, I certainly didn't realize how quickly local area networking would become popular. And by the time the ARPANET project is, actually by the time the internet project is underway, seriously, we're in 1974 or so, we're starting to see some significant Ethernet work happening. And by the early 80s, it becomes very commercial and available off the shelf. So there was a rapid escalation of the number of local area networks. And we very quickly realized that the IPv4 address structure wasn't going to be good enough. And we went through several series of reinterpretations of 32 bits of address, and then finally realized that that reinterpretation was not going to be good enough. And so from 1992 to 1996, the Internet Engineering Task Force had this lengthy discussion about what should be the next generation of IP address structure. Sure. And they ended up with IPv6. And in case anybody's counting, you might ask, what happened to IPv5?
Right.
That was an experiment that involved essentially broadcasting, which did not scale very well, so we abandoned it. V6 was 128-bit address space, 3.4 times 10 to the 38th addresses. Surely that's enough to last until after I'm dead anyway, and somebody else's problem. It turns out that it was not widely adopted. And I've often wondered why, because at the time it gets standardized is 1996. Well, we hadn't used up the V4 address space at all in 1996. But what did happen is that the World Wide Web was sprung on us starting in 91 without a great deal of uptake. By 93, the National Center for Supercomputer Applications develops the Mosaic browser.
Correct. Yep.
Which is highly attractive. It's
a GUI for the internet.
A graphical user interface. You could see formatted text and imagery and made the internet look like a magazine. And the next year, Netscape Communications is created, a for-profit company. It comes out with Netscape Navigator, which is its browser. And then it goes public in 1995. The stock goes through the roof. All of a sudden, the dot boom is on. So what's happening in the 96 period is that we announce IPv6. Nobody pays any attention because nobody's run out of IPv4 address space, and they're all concentrating on how do I make money out of the World Wide Web.
Sure.
And so that goes on until 2000. Then the dot bust happens. A lot of those companies go out of business. In the meantime, people have found various new ways of hacking the IPv4 address space by using private address space and some mappings that are called network address translations.
Right.
So that little local area networks have their own address space, which could be the same as somebody else's, but you never expose those to the public internet.
Right.
You do a mapping into something that's distinct and unique. So the network address translation reduced the demand for new address space significantly. So today we're probably 40% penetrated in terms of who can use IPv6.
Yep.
We think maybe 2/3 of all the traffic on the net is probably flowing on V6 because a lot of the streaming video is going over V6 carriage. Most mobiles are running V6.
Right.
So there's a lot of it out there, but the network is not purely V6. Someday, that's when you can tell you've succeeded, is install V6 and V4 is carried as a tunnel inside of V6.
Right.
We're not there. But so the resistance there was necessity did not drive the uptake.
Right.
Because there were alternatives and everybody was focused on the web at the time.
That makes sense. I haven't heard it explained that way before. We did skip over one of my favorite interim proposals, Tuba.
Oh, yeah.
TCP and UDP with bigger addresses.
Yes.
I wish that had survived at least as a name, but
that my preferences don't really matter here.
Well, there was a big argument about whether there should be any functionality added if you're going to go to the trouble of upgrading to V6. I was on the tuba side generally thinking, let's do the minimum that we can get away with. Other people said no one will adopt it unless it does something new. And so flow identifiers and a few other things got tossed into the mix. And as it turns out, we found alternative ways of making things work. Unfortunately, network address translation has its own set of constraints, and so it's not a wonderful solution. And we've concluded, by the way, just to jump way ahead in our conversation, that if we do build an interplanetary internet backbone, which is definitely underway, that if we use isolated internets, extraterrestrial internets, God, what a great term, that we would use IPv6 exclusively, and that any such extraterrestrial networks would have disjunct IPv6 assignments, so that if you ever interconnected them, say you had multiple networks on the moon run by the Chinese and the Americans and the Europeans and so on, if they ever interconnected them, there wouldn't be any address conflict.
Sure.
So V6 is the exclusive recommendation for extraterrestrial internets. Well, so here we are today. It's 2025. V6 is in use, I would say, heavily in some applications, and as you say, on the mobiles a lot. But it hasn't been taken up as quickly as I had hoped. Now, the whole topic here was where does resistance come from? Some of it is resistance because the need isn't there, or an alternative is easier for some reason, or thought to be easier. Another one is I don't want to learn anything new.
Sure.
That's a different problem. That's people saying, I know how to do this. I've been doing it for X number of years. I don't want to have to relearn. I consider that to be a kind of disease in a society where technology is changing rapidly. And if you're unwilling to learn something new, then you may actually injure your own future.
But even just from a selfish career perspective. Yep.
And so if you think about the recent past, just to give a concrete example, the iPhone shows up in roughly 2007.
Right.
And by my estimate, that's 18 years ago. And just think what has happened as a consequence of the iPhone's introduction.
Sure.
We have billions of them in use. People are relying on them every day. Now imagine that another 18 years goes by. There will be another invention of some kind that will become ubiquitous. You need to learn how to use it.
Sure.
Look how heavily we're very dependent on these things now. The point is, if you have a long career, which is likely because people are living into their 90s and even hundreds, that means that their careers will be 50 or 60 years long or more. And there will be new technologies coming certainly every 20, if not every 10 years. If you don't learn to use those new technologies, they'll become less and less relevant.
Sure.
And the AI world is becoming the next big thing.
Yep.
And people are starting to learn how to use it. And if you resist that, then you'll be less efficient and maybe less creative than your competing colleagues, because this is powerful technology. It's true that it does things that we don't expect or don't want, but people are the smart people anyway are learning how to harness this stuff to be more creative and more efficient. So you have to learn, and you have to want to learn, and you have to know how to learn in order to be current over a long career.
I very well said. And I've seen the smaller example of that just in the network automation realm, where there's been a resistance to, I've done it this way for years. I've been the CLI jockey and I know how to get my routers and switches to work. I'm not interested in learning what even a programmatic approach and using APIs means. And I think we're seeing that amped 10x or 100x with what's happening with AI tooling coming today. For sure.
It's a classic problem. I've made a career out of this. I don't want to have to start over again. Then I'll be a tyro instead of an expert.
Right.
And that's a little disconcerting to begin with. But the smart people will figure out how to use new technologies as soon as possible so that they'll be relevant to business as it takes that technology up and uses it.
And I think those people who are willing to engage when there is a new technology development, there is a lot of hype. And we're not here to, myth bust what's happening with AI here today. But even if only 10% of it is useful, that's still some 10% very impactful or potentially very impactful. And people who are hacking their way through the jungle, trying stuff, are the ones that are going to help us find the right use cases. And, maybe this isn't the right thing for me to use to find the launch power on this optic at 20 degrees centigrade, but help clean up my jumbled bullet points and turn them into a really nice planning document for Vint Cerf before this podcast. Use cases matter, right?
Yeah, they certainly do. And had been very skeptical of the AI functionality for quite a long time. But in the recent past, looking at some of the large language models, it's quite astonishing what they're capable of doing.
I agree.
And even as long as you're alert to the possibility that they got something wrong, sometimes that's hard to figure out, because if you don't know anything about the topic and this thing disgorges what looks to be a very sensible dissertation on the topic,
right?
You can't be sure whether it's right or wrong if you don't know the subject very well. It's like the stories about lawyers who've used large language models to produce a pleading, which they hand to the judge, and the judge says, that reference doesn't exist.
Right.
And your argument is no longer valid. You did not do yourselves a favor.
Getting laughed out of the courtroom would be generous at that point,
yes.
Right? Well, I want to come back to that topic, but let's touch on interplanetary internet for a bit here. And there's one name from the ARPANET era that you haven't mentioned that I heard you bring into focus when we met at SharkFest in Richmond in May 25, I think. And that's JCR Licklider. Can you tell us a little bit about him and his fundamental role in getting ARPANET moving and how this connects to a vision of a galactic network?
So there are two people really who should be mentioned. Well, there are many, many others, of course.
Sure.
Licklider and Engelbart, JCR Licklider at MIT and Douglas Engelbart at SRI International. Each of them in the 50s conceived the idea that computers could be very, very powerful in conjunction with people. So working together,
sure,
the computer could augment the capacity of a human to do things. And if you look at what people do with AI today, there's no doubt in my mind that Engelbart was right. It's just that was 60 years ago. The interplanetary stuff is tongue-in-cheek. That is something we can attribute to Licklider, because in 1962, if I'm remembering right, he's thinking about computer networking, the use of computers to augment people's capacities. And he writes a letter to his colleagues saying, let me tell you about my intergalactic network idea.
Okay.
And so a lot of us remembered that letter. And when we started seriously working on the design and implementation of an interplanetary internet, we decided to remember Licklider by giving his name to one of the transmission protocols, the Licklider transmission protocol, which is a kind of a lower level, link level thing supporting the higher level bundle protocol suite.
Okay. Licklider link layer.
Yes. So we tried to remember JCR Licklider for that. The interplanetary work got started around, well, let's be careful about this. In 1964, NASA decided that it was going to build very large antennas, 70-meter dishes, in order to prepare for deep space exploration.
Mm-hmm.
And it was ambitious and very far-sighted for them to have done that. The three dishes that they built were in Canberra, Australia, Madrid, Spain, and Goldstone, California, about 120 degrees apart, around roughly an equatorial axis. So as the Earth is rotating, those antennas can see into most of the solar system. They knew that they were building this to support multiple missions over time. So it's a multi-mission infrastructure. That was an extremely ambitious thing for them to do. And of course, it's turned out to be fundamental to all of our American space exploration.
Sure.
There are nearer Earth networks like the TDRS system, which is I forget what the acronym stands for right now, but it's a telecommunications data relay service. And there's another near space network that both of which are run by NASA along with the Deep Space Net. But those were all point-to-point links between Earth and a spacecraft, typically. There were some bent pipe arrangements where you transmit to a satellite, and the satellite translates that into a different frequency and passes it on, but it's not stored forward.
Okay.
And it's a very manual environment. You have to plan all the contacts. You have to know which things transmit and when and which angle am I supposed to point the antenna at. So we wanted, in 1998, we wanted to think about how to build a network in space that would be as convenient to use as the terrestrial internet is. And we very quickly discovered that the protocols of the internet were not going to work very well in a deep space environment. Part of the reason for this is the speed of light is too slow. It's 300,000 kilometers per second, 186,000 miles a second,
Sure.
which sounds fast until you start realizing how far apart things are, even in our local solar system.
Sure.
Earth and Mars have distances ranging from 35 million miles to 235 million miles.
Right.
So at the speed of light, 35 million miles takes 3.5 seconds to transit. And of course, 3.5 to come back. That's 7 minutes of round trip time. And when we're farthest apart in our orbits, it's 20 minutes one way and 40 minutes round trip. So as we're looking at our experience with the internet, we realize that the TCP/IP protocols probably don't work very well with a 40-minute round trip time, and it only gets worse when you get further.
It's not going to work here.
Ping is not your friend here.
Right.
So we started thinking, well, how could this work? And there were not only this variable latency, but also disruption, because the planets are rotating.
Mm-hmm.
If you're talking to something on the surface, eventually you can't see it anymore. Or if a satellite goes behind the planet, you can't talk to it till it comes around. Planets go behind the sun. You can't talk to them until they come out from behind the sun. So this is a variably delayed and disrupted environment. And so we concluded that as good as TCP/IP has turned out to be, in a terrestrial environment, it's not going to work for interplanetary.
Sure.
So we developed a new bundle protocol suite, which took into account a lot of those parametric differences. It's been through 7 iterations now. We're in bundle protocol version 7. It's been standardized by the Internet Engineering Task Force and the Consultative Committee on Space Data Systems. It's been implemented and has been running on the International Space Station since 2009.
Okay.
We've done many interoperability tests with different implementations of the protocols with the Korean Space Agency, the Japanese Space Agency, the European Space Agency, and NASA. And literally in this 6-month period, we'll be hoping to build a terrestrial emulation of the solar system internet, running on terrestrially, but artificially introducing the latencies and disruptions and so on. So we can test this at scale. We can start running heavy traffic through it and make sure that our implementations will deal with all the problems that are likely to occur. The Artemis return to the moon mission has already done 1 loop around the moon. The next one will carry astronauts around the moon.
Right.
The third one in 2027 or maybe 8 will land astronauts on the moon. So that's only a couple of years from now, which means that we better be ready with communications capability to support a manned mission of some duration. So we're feeling pressure to get this technology solidly in place, knowing not only that we will need it for the moon, but we'll need it for the subsequent Mars missions. And then as we continue to send robotic missions around the solar system, we need an increasing amount of network capability to command the devices and to get the data back. What's important about all this is that the scale at which we can do this exploration is increasing rapidly because of the cost of lift into orbit is reduced dramatically thanks to companies like SpaceX and Blue Origin and others.
Right.
So that increases the demand for communication. We already know the deep space net is overloaded, and it will just get more overloaded. So we need to have additional networking resources to support a vigorous space exploration program, not just in the U.S. or in Europe or with Japan and Korea, but the other space agencies as well. We've designed it so that multiple parties can implement pieces of the interplanetary backbone. We call it the solar system internet. For the same reasons that that's been beneficial in the terrestrial internet, so multiple parties can build pieces of autonomous systems and then hook them together.
Sure.
We'd like the same thing to be true for the interplanetary system.
Very useful analog, right? Yep.
And then ideally, the people who are using it don't have to worry about the schedule and all this other stuff. That the system figures that out for them. So if you have a command to send to something, you tell us what the command is, and we figure out how to deliver it to the destination.
Sure.
Just like today, you don't worry about, which router did my packet go through. You just assume that it started here and it ended up over there. End of story.
Ping will tell me if I can reach it.
Yeah.
But,
well, in this case, it might take a while for you to discover whether you can reach it. But.
Well, so you have the interplay between the protocol mechanisms that are going into the bundle protocol suite, but there's also infrastructure. And this is harder in space and more expensive, but has there been more thought to get around this satellite's going behind the planet, systems of relays that one is always visible?
Well, there are some efforts to put in multiple relays so that you have visibility all the time. That will certainly be true for the return to the moon, because if those missions are manned, then you don't ever want to lose communication with a live mission, because there could be an emergency and you need to know about it. Now, you have to remember, though, that as we get farther and farther apart, the notion of knowing about a problem now is not a good model, because now on Earth is 20 minutes away on Mars. Right. So we don't experience the same now. We only experience the same now if we're co-located with each other. Right. Where the speed of light doesn't matter. Right. But when we're not co-located, the notion of now is not accurate. Nonetheless, you still need to deal with the possibility that there won't be a continuous connection. Right. And that can happen either because you couldn't put enough resources up, or the resources you put up failed, or maybe one ran out of power, maybe it's in safe mode. So we can't absolutely guarantee that there's always something there to communicate with. In any event, we want as rich an environment as possible to build resilience into the system.
So if I take the analogy or the example of Apollo 11, for example, and it required people troubleshooting and coming up with solutions
in real time,
yes. With a blackout as they go around the dark side of the moon.
Yes.
If I think of scenarios like that where local intelligence was required and was very helpful, and I think about these much longer delay and extremely variable delay scenarios, what if I bring back in the artificial intelligence and autonomy topic here? Are these long distances opportunities to exercise more autonomy in vehicles? How do you view that?
You're forced into exercise. Sure. I mean, even the rovers on Mars, which cannot be steered in real time, have to be told, look, you need to get from here to here, to A to B to C to D. Sure. And we told you where you need to have gotten to. Right. But we don't tell you exactly how to get there. So that's a local decision by the rover.
That's a proven technology, right? We can see that on Earth, and we've seen it with the Mars rovers, right?
Of course, they still get stuck from time to time. I mean, things can happen. But the idea is that a great deal of autonomy is necessary, and that will certainly be true for future space exploration, which is why AI is an interesting possible technology to help us with that. It doesn't necessarily have to be large language model AI or reasoning AI, but it does need to be something that can operate autonomously without human intervention.
I think we do get caught up in the, large language models are taking so much oxygen in the room these days, but there are small language models. There is machine learning, which is still part of this problem domain, and are all useful computational techniques for different types of problems.
Yeah, that's exactly right.
Yeah. I think another interesting challenge here is, we see new GPU hardware coming out at least every year now.
And, or maybe every 6 months. But,
exactly. Way faster than most companies can actually absorb it and amortize the cost.
Yes.
And certainly, if I'm going to launch a vehicle into space that might last 10 or 15 years, I'm not upgrading the hardware every year, let alone every 6 months.
That's all true. And what's amazing, of course, is that the Voyager spacecraft, which were launched in 1979, are still functioning.
Isn't that amazing?
I mean, it's just absolutely incredible. The computers were idiosyncratic.
Right.
They were not off the shelf by any means.
They're not running Unix.
Right. And those things have been, now they're outside of the solar system. They're in interstellar space. And they're about 14 billion miles away, which means it takes almost 24 hours for a signal to get there.
Yeah.
And another 24 to come back. So you're talking a two-way handshake, a two-day handshake.
Sure.
and that's pretty amazing. So, we have, I mean, that's unavoidable.
Right.
But your point about AI being useful in an autonomous way, I think, is exactly right. We will be relying on these things to operate independently of anybody being there.
And you can still have terrestrial model training, whatever the model type is, and get loaded and be useful for years. It's not necessarily, fresh for only 6 months.
Well, yes, certainly we think that the physical equipment can survive.
Right.
We've had good examples of rovers that have lasted a dozen years, for example. And all of them have been capable of receiving updates to the software.
Right.
And so that's very important. We have to be able to update the software to add new functionality or fix bugs that we found. So that suggests to me that robotics may have significant longevity, even though we can't upgrade the hardware.
Sure.
And then think of the Tesla cars get new software updates seems like it's every other day or something.
Right.
To do new things that it couldn't do before.
Right.
That's what we do for the spacecraft as well.
But in a very highly reliable network connectivity environment and relatively high bandwidth.
Well, yes, this is true. Yeah. So but nonetheless, we've demonstrated the ability to do these sorts of things. Right. We did one on Mars in 2004. Spirit and Opportunity landed. They were to transmit data back to Earth at about 28 kilobits a second from the surface of Mars, directly back to the Deep Space Network. And something went wrong with the radios. I don't remember. I thought I heard that they had overheated or something. Okay. So we had to back off on the duty cycle to keep the radios from harming themselves or the instruments on board. So they were going to back away from the 28 kilobits per second that they could support to some effectively lower data rate because they wouldn't run the radios as often. And that made the scientists very unhappy. But somebody noticed that the rovers on Mars had an X-band radio that could communicate with the orbiters that had been sent earlier to map the surface of Mars to figure out where the rovers would go. So it was suggested that we bring some prototype software for deep space communication networking to both the rovers and the orbiters. And we did. We uploaded, 35 million miles or more away, software that did store and forward.
Mm-hmm.
So you could have the orbiter come overhead. The rover would transmit the data that it needed to get back to Earth to the orbiter. The orbiter would hold on to the data until it got to the right place in its orbit to transmit to the deep space net. So that's store and forward packet switching effectively. What was interesting is that they got 4 times more data back that way than they would have gotten from the direct to Earth path, because we had much more rapid transmission to the orbiter, and the orbiter was outside of the planetary envelope, atmospheric envelope, had bigger antennas and more power, and it was transmitting to the 70-meter dish. So we got 128 kilobits from them. The result was more data going back thanks to store and forward networking.
Sure. No, great way to frame that. And a little new spin on maybe a 1 gig link versus a 400 gig long haul link.
I know getting a gig out of a long distance link, optical link, is a challenge. I think the maximum that we've done with optical communications has been about 620 megabits a second from Earth to an orbiting satellite around the moon. When you get further out, you're talking hundreds of megabits a second at best. But that's still substantially better than what you get with a typical radio link.
Sure. That sounds suspiciously close to OC12, sonnet rates. But I won't connect dots that aren't connected. If you, as a little sidebar, if you've got people who are interested in getting involved in this more, at least understanding more, where would you point them?
I would urge them to go to ipnsig.org, ipnsig.org. That's the interplanetary chapter of the Internet Society. It's been in operation since 1998, the same time that the interplanetary network was started. And we have about 1,200 members now scattered around the world. Who are, some of them are very active. They've implemented the protocols. They're experimenting with it, with an implementation of the bundle protocol suite, interacting with each other. Others are just kind of following along. But it's a very active group.
Are there opportunities to get involved in open source aspects of it, or is it all closed?
No, it's all open source.
Great.
Even the NASA implementations of the Interplanetary Overlay Network, or ION, is open source on SourceForge, if I remember right. And there's a lot of activity to explore and expand some of the functionality of the bundle protocol suite. So at this point, there's plenty of opportunity. People have implemented this stuff on multiple platforms, Raspberry Pis and other small devices. And there's work going on at APL. Why do I want to? That's the Applied Physics Laboratory at Johns Hopkins, is working on a full-up bundle protocol-based router for a variety of applications.
That's great. I hope somebody hears this and actually finds a way to get connected and get involved. Again, I think the networking for AI is such a attention grabber. There's other areas of innovation and development that need good people to get engaged. So.
Absolutely true. Now, just looking at machine learning for a second, one interesting possibility is that each rover is out there gathering data and is training a large model to learn what it found. What materials were found, what kinds of rocks, and so on. And you can imagine, instead of trying to transmit all the data back, imagine that you send the model parameters back instead.
Interesting.
That's federated learning. Then the problem is you've got the model's weights, and now the question is, how do you combine the model weights to do something better than any one of them could do? And I think that's an open question right now. But the idea of using machine learning as a way of compressing the data effectively is a very interesting one.
Great combination of problems to solve there.
Yeah.
And as the form factor for GPUs does reduce, it puts even more capability on things we can put into flight. So that's definitely you giving me some things for homework here. Let's steer this into the set of operational problems and just for context for listeners, as we had this conversation about you coming on, you very, very humbly said, well, I'm not really an ops person. I don't know if I'm the right person for this. And I kind of stood my ground and said, no, you're absolutely the right person. And the connection that you made with Jack Haverty, that episode will probably already have published by the time yours does.
That's great. Jack is wonderful.
Had an incredible conversation with him, and he exceeded all high expectations that you set anyway. We've made some jokes about, ping isn't necessarily effective in these long delay scenarios. And, the variability and delay is going to impact how we operate these networks.
That's correct.
And maybe I can draw an analogy of, in the ARPANET, in the early days, there were no separate operators. The people who were developing the mechanisms and the software were the ones actually operating it.
Pretty much, although
in the earliest
remember,
days.
it's a layered architecture.
Sure.
And so the core network was run by Bolt, Beranek, and Newman. The ARPANET was run, it was a single entity, and it was managing the entire network, getting data back or, performance information and the like. The very distributed nature was the people who were building the next layer up, the host-to-host protocols, what we call TCP/IP today, was being developed by a much broader range of people, being implemented by multiple parties, and of course, interoperability testing was important. So I'm not sure where you were going to go with that observation. From the operational point of view, the ARPANET is a single network, but then we had operators running the packet radio net and operators running the packet satellite network.
Heterogeneous networks.
And then we had to introduce operators running the internet.
Sure.
And so now, of course, we have this highly distributed environment, tens of thousands of networks all interacting with each other. Each of them has its own operational component. And they need to be able to see what's going on in the network, not just their own network, but what's happening to the others. So the bundle or the border gateway protocol, BGP, plus a number of network management tools are allowing operators of particular networks to understand the context in which they're operating, what's going on with the networks that they're connected to. So those tools will be needed, or analogs of those tools will be needed to run a multi-network interplanetary system as well.
Right.
Ping, by the way, ping actually, there is a bundle protocol packet called ping, or bping.
Okay.
The only issue is that you don't know exactly when it's going to be back. If you do get it back, the other guy was alive when he sent it.
Sure.
That's all you know.
Right.
You don't even know if they're alive when you receive it, because who knows how long there's been in between.
And so reachability is time bounded.
Yes,
if you get an ICMP echo response or whatever it is in the bundle protocol suite, however long ago, that's all the information.
That thing was alive, but you don't know whether it's still reachable for the next packet that you're sending. It's a very different environment.
Well, definitely something to look into and understand the differences for the next generation of networkers coming up to speed here. What do you think, or if I ask you to speculate on the operations issues in interplanetary networking? We've obviously hit the delay issues. What else is going to be?
There's plenty more. I mean, first of all, there is an entire network management suite of protocols that have been developed. Ed Barine at APL has been largely leading a lot of that work because he's building a router which is going to have to use all that capability. So the management tactic takes into account exactly the problem that you don't have a lot of handshaking possibilities. Right. You need to say, here's all the stuff I need for you to do. Please execute. And so you're sending relatively lengthy, if you like, or complex commands to a bundle router saying, here's how you need to configure yourself. Here's where you need to send tracking data or performance data and things like that. So you need to have the ability for multiple networks to be part of this interplanetary system.
Right.
And the way things work here is not quite the same as the autonomous systems of the terrestrial internet. The
Right.
autonomous systems, you can kind of draw a circle around them. You can identify a set of routers that are gateways to other networks.
Those BGP speakers, right?
Yeah, that's right. And then everybody gets a sense for the connectivity of the internet using the BGP routing tables. This is probably not quite what's going to happen in the interplanetary system. First of all, the links are not fixed. They come and they go.
Sure.
And any particular router could have links to a number of different places, but just not necessarily all at the same time.
Sure.
So its connectivity can be highly varied. The way in which devices in the interplanetary system discover they can communicate with each other is to be part of a contact plan. So the contact plan takes a set of nodes that are configured to know about each other. So they could be from different operators, could operate different nodes inside of a contact plan. So you have multiple parties controlling these things. They clearly have to agree on when is this going to be receiving and from whom, and what parameters have to be present in order for that to work, or when are you going to be transmitting?
Right.
What frequency should you be on? In which direction is the antenna pointing? All kinds of things. So the notion here is that the contact plan determines which nodes can communicate with each other. Some nodes can be part of two different contact plans, or maybe even more than two. If the same node is in two different contact plans, then it could act as a relay between groups of nodes, between effectively autonomous systems. It doesn't have to be. You can imagine a node participating in more than one contact plan simply to be either receiving data or sending data to different places without being a relay between the contact plan members.
Sure.
The contact plans have to be computed. They have to be distributed so everybody knows when it's their turn to talk. There has to be a way of making sure that any node that's going to talk to another node knows at what frequency it should be talking, what modulation scheme, what address, if there is addressing involved. So there's a lot of information that has to be provided to a node in the interplanetary network to know how to use its communications assets when it talks to somebody else. So a lot of this is still in development.
Sure.
And the reason that I want to get a terrestrial analog of the whole system running is that we can see how it works at scale, see how well it deals with excessive amounts of traffic, and we can fix things easily because it's terrestrial.
Right.
And sending somebody to Mars to go figure something out is much harder.
Brings new meaning to the phrase truck roll.
Yes, it does. Yes, it does.
What other operational things do folks need to think about, or paradigms that are just not part of what we know for terrestrial networking?
Well, I think apart from just the basic network operation and being able to get reports back and asking for detailed debugging information, this is happening in the context of commercialization. NASA has offered to essentially purchase habitats, laboratories, rovers, communication service. And the result is that commercial considerations suddenly enter into this picture that might not have if this were a purely national kind of activity. So NASA has offered to buy the product of a moon on the mine. A mine on the moon. And if you wanted to sell moon dust to NASA, they say, fine, we'll be happy to buy it. So then you say, well, can I own the property that my mine is on? And the answer is no. The Outer Space Treaty of 1967 doesn't allow for extraterrestrial ownership, which I suspect eventually is going to have to break. I think at some point we have to accept the possibility somebody could make a legitimate claim for property on the moon or Mars or someplace else. We're not there yet. But even if you're just operating a mine on the moon, what happens if somebody interferes with the operation? Now the question is, in what jurisdiction does a dispute get resolved?
Right.
can you register your mine on the moon? Where do you go to register it? What if somebody actually actively interferes with things? Do you call the Space Force? What's the right thing to do? Well, we don't have answers to a lot of those questions, but those are operational, pragmatic questions about operating in a multinational environment.
No, that's ground that needs to be covered for sure. And we kind of like V6 adoption, we'll get closer to it when we need to.
Something. Although I think we need it very soon because we will be returning to the moon in 2026.
Right.
And there will be habitats, there will be laboratories, there will be rovers, there will be communications, and there will be disputes.
Yeah.
Or there will be emergencies. So there is a kind of a prototypical system that's been developed. It's called the Artemis Accords.
Okay.
And for the Artemis return to the moon mission, which involves NASA, JAXA, ESA, and CARI, the Korean Space Agency, the Artemis Accords are a set of norms about how they will operate.
Okay.
So it's not a treaty, but there is agreement, and you sort of sign up for those desiderata when you become part of the Artemis activity. So that will act as a kind of a sandbox to see what is sensible and feasible for treaty-like treatment, where it's not only do you make an agreement, but there's some enforceability involved.
It's more than a place to start, right? So some progress being made.
Yeah.
That's great.
Yeah.
Well, let's try to tie the past to the future here. Let me throw this at you. From the ARPANET into TCP and TCP/IP days, what are the most impactful design or even implementation decisions that came out of that time that either affects internet operations today or that you've seen impact design decisions that were made for interplanetary net, the bundle protocol suite?
Right. So I would say that first of all, one of the most important decisions was splitting IP off from TCP.
Sure.
And that's around 1977, and that was to handle real-time communication that could tolerate loss. Speech, video, all of those things are capable of dealing with lossy signals. So that's the first big change that happens. Then I would say the next big thing after that is the domain name system, which shows up in 1983, 84, and is needed because the manual distribution of name to address tables was no longer feasible.
Right.
So DNS has turned out to be another major change.
A really big hosts table. Yeah.
Yeah. Then the dynamics of it were really important. Then I would say that's 1984 or so. I would say the next big thing that happens was not a technology, it was an expansion. The 1986 to 88 period brought the NSFNet backbone, the Energy Sciences Network from the Department of Energy, and the NASA Science Internet into the picture, together with what was called a Federal Internet Exchange, or FIX. So the government-sponsored networks, all four of them, including ARPANET, interconnected with each other through the Federal Internet Exchanges. Commercialization hits in 1989.
Right.
And they form a commercial Internet exchange, UUNet, PSINet, and SurfNet. And so all of those are now hooked together one way or another. And the BGP protocols arrive around that time in order to cope with calculating connectivity among all the various networks. Then comes the World Wide Web in 1991, and its instantiation as Netscape Communications and the Netscape Navigator around 1994 or 1995. Let's see, what I would say after that, we've already picked up BGP. V6 is sort of floating around in there, not being terribly deeply implemented. I would say the next big thing that happens in the net is social media. You could see elements of it. I skipped over email, which is 1971.
Right.
Which is a major addition to functionality of the system.
And you played some important roles there with MCI, as I recall, correct?
Well, actually, I can't say we were not around doing anything like that in 1971. That was the
later on.
Yeah. Later on, in the early 80s, we did build MCI Mail with the intent of connecting it to anybody else who was willing to be interconnected.
Sure.
Which at the time was not broadly understood outside of the internet community, which was all interconnected with standard internet mail. So we made sure that the MCI mail system could interface to the SMTP of the internet, and that was a helpful thing to have done. Let's see. So we get to the social media that starts showing up. I guess around that same time, the iPhone shows up in 2007, 18 years ago. And that, of course, has a gigantic impact on everyone because it makes the internet accessible from anywhere you can get a signal.
Right.
And, of course, the mobile phone becomes more useful because of the apps that it can run, relying on servers in the internet.
Right.
So that was an escalating capability, and you have to give credit to Steve Jobs for figuring out this mix of Wi-Fi, 4G probably.
3G, I think, at the first
or maybe
the first
even
one.
3G at the time. The camera, a microphone, a speaker, and a touchscreen display.
Yeah.
Just incredible combination of capability.
I thought I wanted my BlackBerry keys. I really did.
I was very unhappy, and I'm still kind of uncomfortable with the soft displays. I poke at it. I haven't figured out the thumb bit.
Sure.
Which that's another good example of not being able to learn the new things that all the other kids grow up with.
Right. But you seem to be doing okay with that.
Well,
so you've adapted.
I'm still managing.
Yeah.
The thing is that the iPhone just triggers a massive transition, just as the World Wide Web did a few years before, a decade or so before. So I would say that the next thing which is hitting hard is the AI stuff. And that's becoming increasingly useful over time as we learn how to make these systems more responsive and less uncertain in terms of their output.
For sure. We'll start to wind this down to respect your time. But there's one question I ask everyone that comes on an episode with regard to outages.
Yes.
I having not been directly in an operator role, I'm not going to say what outage have you caused, but you must have seen some doozies.
Oh, yes, from all the way back to the ARPANET days, there have been some interesting ones. The most weird ones from the ARPANET period resulted from the fact that the Honeywell machines didn't have any memory protection.
Those were the internet.
They were the packet switches.
Right, the packet
switches of the internet, the so-called IMPs, the interface message processors. They didn't have any memory protection, and so at one point, the IMPs were propagating information about routing. You know, who can I talk to?
Right. Just
like the BGP does today for the internet, and its memory got wiped out. And we didn't notice it because there were no check bits. And so it sent one of them, I forget which one it was, Harvard, Node 10, sent a note to everybody else saying, I'm 0 hops from anywhere else in the internet.
It's like advertising the default route.
The ARPANET.
Right.
And it's sort of like saying, you know, speed of light is irrelevant. I am connected directly to every place in the universe. So all the traffic in the internet hits Harvard. And of course, it falls over. So that was one of the more amusing ones. And it taught us a big lesson about memory protection.
Sure. And really impacting the vendor, the network element community. Sure.
A lot of the other things that have happened, a significant fraction are thumb-fingered mistakes. When you configure things wrong, bad things happen.
Really? Let me write that down.
Right. Yeah. You need a T-shirt. Right? So the problem is that sometimes you can tell by looking at it. Even a piece of software can tell by looking at it that a parameter is out of spec.
Right.
But sometimes it's the combination of parameters in a configuration that cause the problem. And it's not obvious by looking at any one parameter that there's a problem.
Can be syntactically correct, but cause logical problems.
Yes.
Yeah.
So that's one of the biggest issues is a lot of the errors and failures and outages that happen are a result of misconfiguration.
Right.
And it's often, we shoot ourselves in the foot. Now, there is another kind of misconfiguration which takes place. In fact, we're experiencing that with some of our optical fiber cables. People drag anchors through the cable and they kill it. They break the cable.
It's the backhoe, but beneath the sea. Yeah.
And so the problem there is that it takes a while to find where the break is,
Sure.
and then it takes a while to fish the cable up and pull it together and reconnect everything. So those outages are the result of either deliberate malfeasance or negligence, like
Right.
drop an anchor in the wrong place and then drag the anchor. And that's been a problem. The fiber optic networks require a considerable amount of attention to keep them running.
Right. It is fascinating to see Google and others investing in submarine cables and how important that infrastructure is for the normal operations of the internet today.
Absolutely true.
And as we go further out, we're going to discover even more, operational idiosyncrasies that we can't even imagine right now.
I think you're right about that. And this is failure of imagination gets in the way of answering the question, what could possibly go wrong?
Right.
Which is the first question you should ask any engineer who's trying to design anything.
And not ironically.
What could possibly go wrong?
Yeah.
And then the second thing that you often need to ask is, what is it we don't know, which if we did know it would make a big difference?
Right.
And those two kinds of questions, I think, are very critical to good design.
Yeah. Well, what last words do you have, at least for today, for inspiration and people who really want to go deeper in what's happening with new advances in networking? I mean, you've seen a pretty wide span of where we came from and where things are going. What can you boil this down, or at least drop a couple of bombs of wisdom on new networkers?
I don't know whether any of this qualifies as wisdom, but I will say I can remember how excited I was at the beginning of the Apollo program. I got to work on some of the F1 engines for the Saturn V rocket. I wasn't physically working on the engine. I was gathering data from the tests to figure out whether these things would hold up until they ran out of fuel. So it was a statistical analysis, and I was writing the software for that way back in 1961. And at the time, I was tremendously excited. I'm all of 18 years old, and I'm imagining, oh my God, this is really something.
Right.
We're going to be launching these things every 2 weeks and maybe 20 years from then. So I'm imagining 1981, flying cars, every 2 weeks, the rockets would be launched.
Right.
Well, it didn't quite work out that way. But I can tell you that here it is, it's 2025, and I'm incredibly excited about what we're doing here. We are going to build an interplanetary backbone network. We need it. We know we need it. It needs to run in the same very automated way that the terrestrial internet does. And so watching the successful and frequent launches coming out of SpaceX and maybe out of Blue Origin is really exciting. I mean, I feel like I'm 18 years old again. And I wish I were, because I'd like to see what the hell happens 70 years from now. I probably won't make it. But it's fun to be part of the beginnings of all this.
Yeah.
I think that all I can tell young people is that hang on to your relentless curiosity and enthusiasm, because that can carry you for a very long career. I mean, I've been in this game in a formal way since 1961.
Wow.
And so, you can do the math. That's a fairly long career. And I find it as exciting now as it was back then, maybe more so because there's more possibilities coming.
I share your optimism, and I had it before coming into this conversation, and I have it even more now. So Vint Cerf, Chief Internet Evangelist for Google and primary person of interest in all things networking. Thank you very much for your time.
Thanks so much. I really appreciate the opportunity.